Hi, I'm Beth Faber from the Hydrologic Engineering Center, and this is part 3 of the lecture on Monte Carlo simulation. This is the third video of 3. So in our outline, we're now at the applications, right? And we're going to start by looking at flood risk analysis, and we'll build towards the approach that's used in HEC's software called WAT, Watershed Analysis Tool, and its flood risk analysis option. Right, but on the way, we'll be looking at a computation that's also done in HEC's FDA software. Right, so in flood risk analysis, our primary metric is the expected annual flood damage, or EAD. So we've seen that the expected value is just the mean of a probability distribution. So expected annual damage is just the mean of the annual damage frequency curve. Right. So since we're looking at this from a Monte Carlo simulation perspective, we can interpret EAD as the average damage over a long period of time, right? So if this is a long period of time, in most years there won't be any damage at all. In some years there'll be some damage, and occasionally there'll be a lot of damage. And if we average all of these years, including the zeros, we get this blue line. Right? This might not be an amount of damage that ever actually can occur. It's certainly not what we expect to occur, but it is the mean, right? Or the expected value of damage. So this is like the mean of the roll of a six-sided die being 3.5, right? It's not a value that can occur, but it is the mean of the probability distribution, right? So this annualized value of damage can then be compared to annual cost in a cost-benefit analysis. Right, so how do we compute EAD? Well, it's traditionally done by condensing all of our hydrologic and hydraulic and economic analyses into 3 summary relationships and combining those 3 relationships, right? So we have the flow frequency curve that we've been looking at in this class. We have a flow stage rating curve, and we have a stage damage function. Now, since we have flow in 2 of the curves and stage in 2 of the curves, that leaves us with just damage and frequency. So when we combine these 3 curves, we can create a damage frequency curve. The EAD is just the mean of the damage frequency curve. Right? So let's look for a moment at the 3 summary relationships. The first is that flow frequency curve that we've seen a lot of already this week. And I'm showing below the 2 other depictions of probability. So the flow frequency curve is the CDF of annual peak flow. Here we have the PDF and the other type of CDF with the axes switched. I had mentioned that the area under the PDF is equal to probability, but I hadn't mentioned yet that the area between the CDF and the probability axis allows us to compute the mean. Right? So in the frequency curve form, it would just be the area underneath the curve. Right? We're going to use that in computing the average of the damage frequency curve. Right? So now our other 2 summary relationships, we've got the flow stage relationship that summarizes all of our hydraulic modeling, and we've got the stage damage curve that summarizes our structural inventory and our topography. So if we take these 3 summary relationships and line them up so the axes match, so we have flow and flow, stage and stage, damage and damage, then we can see that putting them all together results in a damage frequency curve. And then with the relationship I mentioned for taking the area between the CDF and the probability axis, we can take the area under this curve to get the mean, which is then the expected annual damage, right? So the mean under the area under the damage frequency curve is the EAD. So this is our traditional analysis for EAD. It's a risk analysis because we've combined probability and consequence in estimating EAD. So how would we go about changing this analysis into a Monte Carlo simulation? Well, to do that, the probability distribution that we'd be replacing with a random sample is this flow frequency curve. Right? So by generating uniform 0 to 1 values, we can put each uniform value as the exceedance probability, come up to the curve to get a flow, come across to get a stage, down here to get a damage, right? So for every random flow, we get a random damage. That's 1 sample member. With a large sample size of flow, we get a large sample of damages, right? The average damage is the EAD. Right? So let's see what that looks like with a large sample. So we've replaced our flow frequency curve, let's say with 1,000 flows. So here it is in the PDF form, a histogram of flows. And here it is with the frequency curve form, right, to show the CDF. So this is each of our 1,000 flows plotted against the plotting position, with the plotting position based on 1,000 sample members. So now for each of these 1,000 flows, I can compute a damage with my summary relationships, and so I get 1,000 damages. Here's my histogram of damage. Most of them are 0. Here's damage in the CDF form. To get the EAD, I just compute the mean damage, right? So that is my EAD computation as a Monte Carlo simulation. So let's think for a moment, how does the result of doing this computations of Monte Carlo simulation differ from the original computation that just combined the 3 summary relationships? Right? Well, if we've done a good job, there's no difference at all. Right? If we had a large enough sample size of flows, we'll get exactly the same computation of the expected annual damage that we got by combining the summary relationships. Right? So what was the point of doing this as a Monte Carlo simulation with event sampling? Well, the benefit is that when we're replacing the probability distribution with individual sample members, we can bring our watershed models back into the analysis. So computer power has increased quite a bit, and it's very possible now to simulate each individual flow event, right? So for every flow that we can pull off the frequency curve, we can transform it to a hydrograph, and then route it through our reservoir analysis, our channel hydraulics, levee behavior if there's a levee to get stage. Then if there's a levee breach, or if there's no levee but flow gets outside the channel, we've got a spreading model, do inundation mapping, use our structural inventory and compute damage to structures to compute a damage, right? So for each event, each sample member, we get damage. And again, we end with a large sample of damages from which we can compute the average or expected annual damage. Right? So by going to a Monte Carlo simulation, it allows us to bring all of our complex modeling back into the analysis rather than having to just simplify it into the summary relationships. Now, there's even more benefit to this approach when we're looking at modeling an entire watershed rather than just one particular damage site. Right? Modeling an entire watershed, we can see the impact of a levee breach on one event on the flow downstream. If we've got a damage area that has streams on 2 sides, we can see individual events that might flood it from one side or the other side without double counting our damages. So there's a lot more benefit when modeling a complete watershed, but the picture gets a lot more complicated. Right? So this depiction is just showing it for a single damage site. So what about knowledge uncertainty? So what we've looked at so far does not incorporate any knowledge uncertainty. It's looking specifically at natural variability, right? Replacing the flow frequency curve with a sample is fleshing out the natural variability in annual peak flow. We don't yet look at any of the uncertainties, right? We have uncertainty in model parameters in both the watershed models and the probability distributions, and that's not yet been incorporated. Right, so a quick reminder of the difference between natural variability and knowledge uncertainty from our introductory lecture. Right, so a natural variability is also called aleatory uncertainty, and this is just variables that are random and unpredictable by nature. Right, they vary in time or in space. And we also have knowledge uncertainties, which are called epistemic uncertainty. And these are variables that don't change necessarily with time or space, but we don't know their values accurately. Right? Both variability and uncertainty are described by probability distributions. And note the colors that I'm using here, natural variability in green and knowledge uncertainty in orange, is a color coding that is going to continue in the next few slides. Now let's look at how natural variability and how knowledge uncertainty each affect the EAD computation. Right. So the reason that we even compute an expected annual damage is because we don't know what the future values of floods are going to be. And so we don't know what the future damages are going to be. And all we can do is refer to our best estimate of the probability distribution. So we compute an expected annual damage because we don't know the future. Right? So all of our natural variabilities in our analysis are going to be part of the damage distribution. All things that vary in time and space and from flood event to a flood event are going to be part of the annual damage distribution, right? And so they're going to be part of the mean of annual damage or the expected annual damage. So these are things like flood magnitude, the starting reservoir storage, maybe bridge debris, things that will change from event to event. Right, then the knowledge uncertainties, on the other hand, these are parameters in the watershed models. Maybe they're parameters of our probability distributions of natural variability. There's anything in the analysis that we don't know well. And so each of these things is going to affect what the damage distribution looks like. And of course, we're looking at the damage distribution as a PDF here instead of a CDF. Each of these damage distributions I'm showing has a different mean. And each of these knowledge uncertainties is going to affect the shape of this green damage distribution and so affect the mean. And these are things like flood likelihood, our hydraulic coefficients, foundation heights of our structures. Right? So the fact that we have these uncertainties that each is going to affect the damage distribution itself and thus each affect the mean or EAD means that we have a probability distribution of EAD. Right? The knowledge uncertainty is going to cause spread or uncertainty in the value of EAD. Right? So here's the EAD distribution, and I'm going to turn it orange because it reflects the knowledge uncertainty or is caused by the knowledge uncertainties. So what we're aiming for is this distribution of expected annual damage created within the Monte Carlo simulation by a large sample of expected annual damage, right? We create that large sample by replacing all those distributions of variabilities and knowledge uncertainties by samples. Right. So how can we do knowledge uncertainty and natural variability separately because they are different in the way they impact the EAD? Well, we do it using a nested Monte Carlo. So we're going to sample instances of all of our natural variabilities as flood events, right? Sampling enough flood events to flesh out all the probability distributions. And that is going to be an inner loop in our Monte Carlo simulation. And within that inner loop, we're going to compute a value of expected annual damage, right, from all of the events that were needed. And we're going to also sample instances of our knowledge uncertainties as an outer loop, right? So we're going to also be replacing the distributions of knowledge uncertainties by samples. And so the outer loop comes first, and we take one instance of each of our knowledge uncertainties, use it to parameterize our models and our probability distributions to then go around the inner loop, producing as many events as are needed to estimate an EAD, right? So this one time around the outer loop, right, with one sampling of all of our uncertainties is what's called a realization. And so for each realization or each outer loop, we have many, many inner loops to produce the EAD estimate. Right? What this looks like in the sampling is instead of sampling my flood events off of the original flow frequency curve, I'm going to sample a new flow frequency curve from within its uncertainty. Right? I'm also going to be sampling all of the uncertain model parameters within my watershed models. Right? Then once I've done that, now I go to my inner loop and I sample flood events, right, and all the other variabilities that might occur within the watershed, like reservoir levels, right? So now I'm sampling my flood events off of this orange curve, and I'm still going to sample enough events to compute enough damages to compute an expected annual damage. That's one realization. So for each realization, I have an EAD estimate, and then after doing many, many, many realizations to flesh out my knowledge uncertainties, I'll have a distribution of EAD. Right? So to look at that in kind of a more summarized way, for each realization, I'm going to have a distribution of damages and therefore a mean damage that came from fleshing out all of my natural variabilities. For that realization, I had first sampled my knowledge uncertainties and had one instance of each of my knowledge uncertainties to compute this mean or EAD estimate. And then after doing all of my realizations, after doing many of the outer loops, I will have a large sample of EAD estimates to inform my EAD distribution, right? So the EAD distribution is going to be spanning the knowledge uncertainties.